Okay. Hi, everyone. Thank you for joining us. Thank you to our speakers for joining us as well. And today we have for you two more exciting talks on high energy astrophysics. As Peter said, this is being recorded for anybody who slipped in between the 2 seconds and he stopped talking and I started talking, so please be mindful of that. And without further ado, let's get started. So our first wonderful speaker today is Dr. Alexandre Marcowith. He finished his PhD in 1996 at Grenoble University. After that, he was a postdoc fellow at Max Planck in Heidelberg, and then in Utrecht. Afterwards, he went to CNRS in Toulouse as a researcher at the IPAC laboratory. And finally, in 2006, he moved to Montpellier University as a staff astrophysicist. So his main research field is the kinetic theory of astrophysical plasmas, especially the accretion and transport of cosmic rays in turbulent magnetized flows. And he's a part of the high energy instrument HESS and CTA collaborations. So please take it away.
Thank you for this nice introduction. So I hope you can hear me well and you can see my screen either well. I will go to the full screen. So today I would like to talk about so energetic particles and cosmic rays in young and active stellar objects. So this is a subject I started to work on a few years ago with some collaborators you can see here. So by young and active stars, I will mean today mostly, in fact, T2 stars, so which are solar-like stars, and as you may know, there is a sequence for different class of this object, depending on the degree of evolution. So starting from the star which is quite enshrouded in the envelope in the class 0, and then star producing some jets on a accretion disk settled on, which are class 1 and class 2, and then after, let's say, 10 million years or so, you reach the class 3, so with mostly the star living and an accretion disk around. And if you go to more inside this complex machinery, you will see, in fact, a star which is in rotation, which with its own magnetic field, and surrounded by an accretion disk, also with some magnetic field. And from there, you can launch some disk or stellar wind up to some rather large distances, about 10⁻² to 1 parsec. And so, of course, T2 stars are not the only stars showing some activity, especially at X-rays. And another well-monitored category is M dwarf stars, so which lie in the let's say right part of this Hirschsprung-Russell diagram. So that these are relatively cool stars and with low luminosity, but they show
Alexandre, sorry for interrupting. Are you advancing the slides, because we see still the first slide of the presentation?
I don't know. So can you see it now?
Now we see a different slide. Yeah.
It's because the full screen is not okay. Sorry for that. So what did you miss? So I was presenting mostly the T2 stars, so the sequence.
Okay.
And saying that it is so composed of a star and then an accretion disk, and so producing jets. But so also, I mean, you have active stars which are M dwarf stars, and they are peculiar because through the Zeeman Doppler imaging, you can deduce some magnetic field associated with this star, which can be quite high, up to, let's say, 1 kilogauss. And these are of interest because the protostellar disk and the planetary system associated with this star is a kind of scale down of our own solar system. And this star and the planet in this system are more subject to the influence of the stellar magnetosphere because they are closer to the star. So coming to my point of today, so energetic particle in this object. These particles are of interest for several reasons. First of all, energetic particles can produce some ionization at high density columns where radiation cannot penetrate. And so ionization is an important aspect of, because it is a way magnetic field and matter can get coupled. And then accretion ejection physics is likely controlled by this level of ionization. And planet atmosphere, also ionization is important for a later stage of the object. Also, ionization means that you can hit the locally the medium. Energetic particles are interesting also because they can produce some light element and through spallation, and can contribute to meteorite irradiation. They can be probed either by radio emissions, synchrotron radiation, as we will see in 1 minute, and possibly through gamma rays. So by energetic particle, I will now argue in favor mostly of in situ particle accelerated, not exactly cosmic rays, which are, let's say, background energetic particles in the interstellar medium. I will show you why we need some in situ particle acceleration in this object. Going towards observation about non-thermal processes in T-theory system, I can show you some interesting examples. The first of one is the derivation of high ionization rates in at least 2 objects, which are quite different each other. The first one is OMC2 FiO4. So it's a proto cluster composed of intermediate and solar mass stars. And thanks to Herschel observation, which where people were able to derive the abundances of HCO plus and N2H plus ion species, if you calculate the ratio of these 2 abundances, you can calculate the cosmic ray ionization rate here. And what is found in this object, in the envelope of this object, so either the warm one or the cool one of more external, is that in fact the ionization rate is about 10⁻12 to 14. That is, let's say, 4 order of magnitude higher than the typical Spitzer value, which is about 3 × 10⁻17. So something quite energetic is going there, taking place. Another example is a bow shock of a T-theory object, and there, using the same type of Herschel observation, and also using also the abundances of element produced behind a shock. So Podio et al. Were able to deduce ionization rate of about 3 × 10⁻16 per second. So that's still 1 order of magnitude above the standard values. Another hint of non-thermal particle presence in this object is through the jets. So here I show you some non-thermal emission. So for one object, which is HH8081, which is actually a high mass young stellar object, which produce strong radio jets, and which has been monitored with G Valley at 4 to 6 gigahertz. And so people were able to derive some maps, radio maps, where it shows so the the radio index moving to positive values likely associated to free emission to negative values which are linked with synchrotron emission. And so which is the index is correlated with the size of the jet, so it makes me think about effects of local emission shocks. So behind this shock, you can produce energetic electrons which radiate in synchrotron process. Going towards the star itself and the accretion disk around it, it's much more difficult to have a probe of non-thermal particle production, because if you want to rely on X-ray flare shows up mostly thermal component. But there are some observations on non-thermal emission in the radio domain, and I show you here two examples. The first one is a DQ TOW, which is a class 2 object. In fact, it's a binary system, so maybe a bit peculiar, which shows a variability of our timescale in the non-thermal emission and also circularly polarized emission. And there is another example of this object, RS5b, which is class 1 object, which shows either circular polarization and flares. And this aspect could be of interest for the coming facility SK, the Square Kilometer Array and radio wavebands. To make short story, which start to be long, so there is a growing interest of looking for energetic particle acceleration in these objects. So here I selected a couple of articles. So you can see that in fact it's a rather starting to be active field with several publications within the last 5 years. Some takeaway message from these works are the following. So if you consider only external cosmic rays, so cosmic ray coming from the interstellar medium, you can calculate a minimum amount of ionization in a circumstellar disk, which is about 10 to minus 19 to 18 per second. So this is a result by Isidore Cliffs and a collaborator. Then if you add some in situ particles from stellar flares with enhanced flux, then you can produce enhanced ionization with respect to this level, of course close to the stars. And also you can amount for some abundances of aluminium 26. So these are recent nice works by Brandt and Hoffner. If you cumulate the effect of energetic particles into protostellar cluster, you can try to explain this ionization rate in OMC2 FiO4. Again, it's a Brandt-Hoffner result, another article of 2018. If you want to deal about ionization in accretion disk, you have also in some stage to account for high Coulomb densities. So here only energetic particle can go there, but then the calculation of ionization start to be complicated because in fact ionization is not produced by the primary particle but by secondary particle, electron-positron production, and particle have also complex particle diffusive path. So this is a result by Padovani and collaborator. And of course, as I told you, T-Tauri stars are not the only one. And M dwarfs are also quite active objects, and the impact of our planets has been investigated by Federico in one of his papers. Then I will move to work done with my collaborator, which has mostly focused on jets, but also a bit on the protostellar surface. So this is a series of work we did. So for short, our model is the following. So we have here you can see a sketch of T-Tauri object. Of course, it's a theoretic view of this object. It's quite simple. So here we argue that energetic particles are accelerated at shocks through diffusive shock acceleration in the Fermi first order process. And so we identified several sites where you can accelerate particle, either at accretion shocks through accretion column over the stellar surface, or shocks in the jet here, or the termination shock, where the jet interacts with the interstellar medium. For each of these sites, we identified the shock speed, the temperature of the medium, the density, the ionization fraction, and the magnetic field from literature or modeling. And this allows us to calculate the particle distribution, which can get accelerated at these shocks. With this, we can try to explain the observation I just showed you before. So turning back to ionization fraction calculation in these two objects. For this OMC2 FiO4, what we did is to invoke particles which are accelerated at the shock on the stellar surface and then propagated toward the envelope, either following a ballistic motion, so diluted as r-2 with respect to the distance of the star, or r-1 if they follow a diffusive path. And these two paths encompass the observation. But then for what concerns the bow shock, here just please look only at the green curve. In fact, you have here is the ionization rate calculated from the jet propagated in this object. And so in order to reach the observation, we absolutely need the help of in situ particle acceleration accelerated at the termination shock. In fact, if you rely only on background cosmic rays, you have it's not enough. So you need really an in situ component. So we then further with Marco on this object, providing possibly another interpretation of this ionization rate. In fact, what we make a try recently and submitted paper is that we try to explain, in fact, both ionization and radio data, which have been found from so a nearby object, which is FiO3, and from between these two objects, FiO3 and 4, you have a jet showing non-thermal radiation, and along this jet you have this site of high ionization rate. And so we try to explain, in fact, both using non-thermal particles. So ionization rate fix the non-thermal particle distribution normalization. So here you see in the space of the fraction of the kinetic energy imparted into the energetic particle and the shock speed, there is a teeny space where you can explain the observation. And once we have the normalization, we try to fit the non-thermal radiation, and so we succeed to do it at the same time. So it possibly suggests that this jet can explain, in fact, non-thermal particle accelerated in the jets can explain both features. A bit of prospective work then for more massive star, we consider also the possibility to reach higher energies, because there the shock are faster, and then we expect to have a particle energy reaching let's say a fraction of TeV. So this opened the possibility to investigate this object with gamma ray facilities, and one of the next one, especially the Cherenkov telescope array. Even if the maximum energy here is a bit at the edge of the threshold, close to the threshold of the instrument. Of course, these results have some uncertainties, and I think it's still worthwhile to investigate investigating this gamma ray possibilities. So before concluding, I just want to go back to star and disk and going towards more, let's say, speculative aspect, because they are not associated with any observation yet. So here is a sketch of this, the inner part of the object with the star, which is rotating, and its magnetic field. And so you have magnetic field line anchor in the disk. And of course, so I told you about so the shock on from the accretion column on the stellar surface, but there is also different ways, in fact, many other ways to inject non-thermal particles in this system. And I especially think about, of course, flares from the stars on coronal mass ejection. But also, as you have magnetic field involved, so you can have interaction of the magnetic field from the star itself and the disk, which can lead to magnetic reconnection events. Or then also you can have magnetic reconnection further away in the stellar or disk ring interaction. Or also, if the accretion disk itself has some level of turbulence, and as soon as you have some magnetic field, if you have some turbulence, you are able to produce some reconnection event, possibly. The level of turbulence of magnetic accretion disk is found to be rather low in the outer disk, but in the inner disk, things are still open, and this basically near infrared data, which can help to constrain this level of turbulence in the inner disk. So just a project, an ongoing project by a PhD student here in Montpellier, is Valentin Brune. So we started to investigate the impact of reconnection events or disk and jets. And so basically what we are doing is, so we assume some reconnection event at some position over the disk. Here is a disk solution obtained with the Prodimo code, which is a chemistry code, which calculates species abundances once you know the type of star. So you have a radiative transfer, and so coupled with chemistry calculations. And then so we can have the density profile, and then we inject non-thermal particle which follow the magnetic field line. And as the particles are moving towards the disk, they will lose some energy through either Coulomb losses and then ionization, and then the losses will carve the low energy part of the particle distribution, as you can see here. And while moving towards the disk, particle will so ionize and deposit some heat. And so the idea would be to test if this type of events, or let's say succession of events, can have some impact over the dynamics of the accretion, and also on the ejection, because if you hit the plasma, you can also ease a bit more the ejection of matter through the rotation of the magnetic field. So that's basically my conclusion. I don't know how much time I took, but so what I want to give you some message. So the following. So you have non-thermal emission tracers, which are radio synchrotron emission and possibly gamma rays, so which are interesting prospect for SK and CTA in this object. I try to show you that energetic particles can help to explain some enhanced ionization rates in some objects. And what is I think it's mandatory is that in situ source of energetic particles are mandatory if we want to explain this data. More speculative work is on the internal machinery of star, disk, and jets. So as I show you, you have multiple scenarios to inject such particles. Now we are not sure that they may have any dynamical effect. But I think it could be nice also to look for more observation and especially multi-wavelength studies of these objects, combining, for instance, HST and Chandra data could be very useful as for this recent nice publication by the Boston group. So really, thank you for listening, and sorry for the start of the talk.
Thank you very much for a great talk. No worries on the start, we got on track. Excuse me, and thanks to the people who pointed out that they couldn't see the slides as well. We weren't sure if they were supposed to be advancing yet. So if you have any questions, we do have time for a few questions, so please raise your hand or put it in the chat. To start off, we have one question in the chat from Federico. At these large densities in the circumstellar medium, is the cooling time of the plasma large enough that the shock can be assumed to be in adiabatic regime, or do you need to assume a radiative regime?
So yes, we calculate this so in the protostellar surface, it is so we evaluate this with Marco, and we found that so first of all that the shock is collisionless. This is the first point. And so I think, yes, we found that the shock can still be adiabatic, yes. But in fact, yes, radiative shocks also may produce some particle acceleration. I don't know if this is what you have in mind, Federico, behind that.
You know, I just wanted to ask with the regime, so you can use the standard, if you can call it standard DSA, or the.
Yes. Okay. Yeah. Yeah. Yes. It's
really important here. So the collision. So you say if you're already collisionless, probably. Yes, it's already.
Yes, it's collisionless.
It's already an answer. Yes. Thanks.
All right, thank you. Any other questions? I don't see any further questions. Well, if you would like to speak to our speaker, we have a few slots still open on his meeting schedule, so please go take a look at that. Thank you again for a great talk, and Peter, on to you.
Thank you.
Yes, thank you, Alexander. Our second speaker is Susanne Aalto. She is a professor at Chalmers University of Technology in Gothenburg, Sweden, where she also earned her PhD in 1994. She was then a postdoc at the University of Arizona and then Caltech. Susanne is currently head of the division for the Department of Space, Earth, and Environment at Chalmers. Her research is focused on radio and infrared studies of starburst galaxies, AGN outflows and feedback, and astrochemistry.
Great, thank you so much for that nice introduction. I actually just stepped down as division head. Yay! Back to science. So today I'm going to, for those of you who've seen my abstract, you might suspect I have delusions of grandeur. I got a bit carried away, so it's a bit long. So I'm going to focus today's presentations on, in particular, the object that we call the cons, and show you a couple of examples of the feedback processes we see from those. So let me see if I can share the screen. There we are. Short crash course in Swedish for those of you. Can you see my slide? Yes, I see some nods. Excellent.
Yes.
So today we're going to talk about thickets as thieves, unveiling the most compact and obscure nuclei. And although I do understand that most of your high energy astrophysicists, this might be a bit of a shock because it's quite tricky. We're going to actually have to use molecules to probe these high energy phenomena in quite a shocking way. Okay, so here's my outline. I just switched to the outline. I hope that worked out. I don't see any shocked faces, so I suppose so. So a quick look at dusty nuclei. Why do we care? And why do we want to use molecules as tools? Some of you may not be familiar with that. An example, one of the most popular AGN tori, NGC 1068, and then we'll move on to the CONS, the compact obscure nuclei. If there's time towards the end, we'll take a look at dusty feedback and the surprising radio quiet molecular jet in the very unassuming galaxy NGC 1377. So why do we care about dusty galaxies? Well, luminous and ultraluminous infrared galaxies are dusty objects. They're often interacting, and they're fundamental to our understanding of galaxy evolution because these objects hide some of the most active evolutionary phase of these galaxies, even at high redshift. We have a surprisingly large amount of dust even at high redshifts. So we need to study these dusty objects in order to understand this very important phase of galaxy evolution. Other important dusty evolutions, of course, AGNs, active galactic nuclei. I'm sure you do know that acronym, where we have growing supermassive black holes, very often surrounded by dust, obscuring their inner regions close to the black hole. So we need to study these dusty objects also to understand how the starbursts and AGNs are connected to each other, and also how the small scale obscurations, which is something one is often detecting, or at least is suspecting to be often detected in X-rays, how is that linked to the structures we see on larger scales of about 10 parsecs? All of these hidden activity is also driving mechanical feedback in the form of molecular winds, cold molecular winds, hot winds, jets, and outflows. So, but one of my preferred tools in order to probe these objects is to use molecules. Now, molecules, back in the day, for an extragalactic astronomer such as myself, we had to resort to using only a handful of standard traces. Cr, carbon monoxide, we used that to probe the extent and the structure of the gas, probing in what in my world is low density gas, with about 100 molecules per cubic centimeters. We used them again to probe where the gas was in galaxies. If we were lucky back in the day, we also had access to polar molecules such as AC and ACO+ that we used to trace denser molecular gas, so density is about a couple of orders of magnitude higher. We can then probe closer to the AGNs and also probe gas that was in fact involved in star formation. And this is, of course, because some of you probably know the cold H2 molecule is a silent molecule. So we must use tracer molecules to probe the cold molecular gas. So this was back in the day. Now we have a much larger number of molecules, even extragalactically, at our disposal that we can use to probe all kinds of activities, the impact of star formation, for example, on its surrounding gas, and including the AGN activities. So we can study then gas distribution dynamics, get dynamical masses in very obscured systems, look for non-circular motions out and inflows. We can, through combining molecules, and in these days, since we have the ALMA telescope, also with the fantastic resolution, we can probe physical conditions, temperature and densities, for examples, cloud stability. We can also see what the impact of the radiation field is on molecules, directly on how they excite the molecular emission, for example, probing dust-embedded sources, which I'm coming back to very shortly. But we also have an emerging field now, extragalactic astrochemistry, where we can use the molecular properties to understand the link between, for example, the growth of black holes and the evolution of the surrounding star formation. We can even study the chemistry in outflows from driven, for example, from accreting supermassive black holes. And this is a very recent development, I'd say the past 5 to 10 years. We can use these molecules also to probe hidden cosmic ray fluxes. We heard an example before in the previous talk on how we can use molecular ratios to probe the cosmic ionization rate, for example. We can even probe stellar enrichment and dust to gas processes. And there's an ongoing effort to benchmark the most key diagnostic molecular species and lines. And a very popular one for people who try to find buried AGNs is to use the HCN to HCl plus line intensity ratio, where an elevated HCN luminosity in relation to HCl plus is supposedly indicating the presence of an AGN. This interpretation is not uncomplicated, unfortunately. Very few things are. And just to show you sort of a quick glimpse on the tools we have at R, this is a fairly old slide I stole from the University of Cologne, just showing that by now we have more than 60 different species of extragalactic molecules detected outside our own galaxy. So this is a growing field, and its importance is increasing day by day. The importance of astrochemistry and molecules as a tool is increasing day by day. So what about dusty nuclei? Well, the dusty torus is a complex structure going from subparsecs to tensoparsecs, and which our view on it is changing now from a fairly static, simple edge-on structure to a dynamical, changing structure governed by inflows and outflows. So instead of being this very simple structure, we see that it's evolving dynamically, continuously, where the outflows and failed winds, for example, inject turbulence into the disks, and we have infall structures that also affect the properties and dynamical properties of the torus itself. So it's a dynamic structure. It's much more complex than we have previously realized. See if I can move on my slide. Here we are. And of course, you can't talk about dusty tori without giving the example of perhaps one of the most famous Seaford galaxies, NGC 1068, where high-resolution observations with ALMA, for example, shows the power of this instrument in really studying the dusty structures and molecular-rich structures close to the accreting supermassive black holes. And of course, to me, close is to be within, if you're getting within less than a parsec, in my world, it's still actually quite close. And this is, of course, because the molecules are not surviving all the way in to the accretion disk. But these studies reveal then these tori, this complex, not very simple looking tori with the sizes of a few parsecs, and complex dynamics, suggested counter-rotation structures that could be real or could be a superposed effects of inflow and so-called outflowing torus. So even though we get this very, very exquisite resolution, it's still quite difficult to completely determine what's going on. But one thing we're clearly seeing as we get closer is that the column density that we can detect in molecular gas is increasing as we get closer and closer to the nucleus. So we're getting closer and closer to the size structures that are being probed with the X-rays, which for this particular object is, I believe, indicating a column density, not necessarily in H2, but maybe ionized gas of 10 to the 25. But we're getting the two fields, if you like, are getting closer and closer to seeing the same kinds of structures. But 10 to the 23 in gas is not particularly spectacular if we compare that to the compact obscure nuclei they recently discovered. So the really opaque nuclei, the cons, have column densities in H2, molecular column densities in excess, way in excess of 10 to the 25, and AVs way in excess of 1,000. And some We're now finding, I'm going to give you some numbers very soon, that some ULERGs harbor cons, actually quite many of them. And they're so thick that they are obscured even in X-rays and in the mid-infrared. As we shall see shortly, we have indications that they're quite common in ULERGs, and they're extremely important, an extremely important piece of the puzzle to understand this unexplored obscured phase. We need to understand them in order to fully map out the AGN statistics and the statistics of hidden growing supermassive black hole and how they relate to the growth of the nuclear stellar spheroid. Recently, we also started discussing and exploring the possibility that these objects could also be interesting sources of cosmic neutrinos. And we're also working on relating these obscured objects to distant dust-absorbed galaxies, SMGs and dogs. Here's an example. This is NGC 4418. The cons tend to be residing in quite boring-looking host galaxies. This is no exception. And the shock with this one was to discover an optically thick continuum at 0.8 millimeters wavelength, which suggests for the standard gas-dust ratio of column density in excess of H, in excess of 10 to the 25. But it's going to get worse. So how do we probe these objects? Well, it is difficult to use, for example, X-rays, which is usually one of the go-to methods we use in order to probe obscured nuclei. But we can use how the molecules connect to the surrounding radiation field and look for vibrationally excited, for example, HCN. Here's an example where we have a high surface brightness mid-infrared field that's exciting the vibrational ladder of this molecule, which then has transitions that we can observe at long wavelengths. So this molecule becomes a proxy for buried, embedded, high surface brightness mid-infrared core. So we cannot observe directly in the mid-infrared because of the massive obscuration. And when I said that it gets worse, I was thinking of this object. This is IC860, again, a rather unassuming object. We see it here. This is taken with a Nordic Optical Telescope. But when we point our radio telescopes, our millimeter telescopes, this galaxy, we discovered something quite extraordinary. Now we use, remember what I said in the beginning, we use HCN, for example, as a probe of dense molecular gas. Now that's not usually strongly affected by opacities on the scales of whole galaxies. But what we found here is that these very common molecules, the opacities on those are so high that they are completely self-absorbed, even in large stretches of scales of 50, even up to 100 parsecs in the center of these galaxies. We can use vibrating studied HCN to detect the extremely hot dust in the center of this galaxy. But even here, what we see here is, again, a rather unassuming image, but even the vibrationally studied HCN is absorbed towards the center, and this is largely continuum absorption. Gas densities are very high. Temperatures are in excess of 250 to 300 Kelvin, which to me is a high temperature. But I think the most shocking thing with these objects is the fact that not only is the continuum optically thick at 345 gigahertz, it's optically thick down to 1 millimeter, and for this specific case, also at 3 millimeters. This means that we're now looking for standard gas-to-dust ratios, column density in excess of 10 to the 26 in molecular gas. It's a brick wall. And these objects are extreme even by galactic standards. We don't really have anything in the galaxy that would correspond to this. So what's hiding in here? Something very energetic is hiding because we have very high surface brightnesses that we can detect using the vibrational lines. So either these are fast accreting supermassive black holes. They're in a phase where they're almost completely obscured and very difficult to study with any other method. Or what we're seeing is a starburst consisting, in this case, basically only on massive O stars, because that's the only way we can fit the mass budget, which means we would have an extremely skewed initial mass function. So these objects are very mysterious. They're massive inflows on their centers, but they also even have outflow structures, which is actually quite surprising. We don't know what the dust to gas ratio is in these extreme environments. We're trying to find out ways and methods on how to test that. We don't even know how much shorter wavelength emission is really leaking out. That's another thing we also try to understand. But the chemistry here is extremely rich. Means that we can use molecules such as, in this case, HOC+, for example, the isomer of HCO+ that we heard about before, the prebiotic molecule methanamine, for example, to help us reveal cosmic ray fluxes and X-ray eliminations in the centers, and hopefully then arrive at the conclusion on the nature of the buried activity. How common are those? Well, our conquest survey aimed to find out through surveying 38 nearby ULUGS, LUGS, and low luminosity dusty galaxies in multiple species, but of course the vibrationally excited HCN as the prime species. The first paper is now out, and we find that the cons, the previously undiscovered cons in ultraluminous infrared galaxies, are very common. Around 30 to 40% of the ULURGs have these kinds of extremely opaque structures at their very cores, and around 20% in the luminous infrared galaxies. Below that, they seem to disappear, and we don't know why as of yet. And there I heard a little tickling, so I'm going to try and move towards the end of this presentation. So the con hosts seem to be major mergers or minor mergers. So there's a link to interaction. But this is something we still have to determine. They have collimated dusty outflows. So they don't seem to be statically in this extremely obscured phase, but they seem to be in this phase long enough to impact the statistics of ULURGs and LURGs. So let me conclude in my last couple of minutes with the feedback processes in these objects. This interesting thing with the feedback of AGN, the cons, is that they tend not to be clearly visible in the far infrared, largely because of the massive obscuration. But when we look at them at millimeter or centimeter wavelengths, what we find, in the case we're up to 20, is a very dense and fast and collimated outflow. So the outflow is collimated and not wide angle, which is usually what we found before for dusty objects. So they are clearly in a different kind of feedback process than more normal, quote unquote, dusty galaxies. And they're obscured in the far infrared to some degree at least. And here's another case where we find line wings of fast outflows when we move to centimeter wavelengths with a VLA using the OH molecule. So the feedback is quite compact, often collimated and obscured. I think the most spectacular example of such a collimated outflow is this, again, very unassuming galaxy. This is NGC 1377. It's a small lenticular galaxy, boring looking in the optical, but has a spectacular silicate absorption feature and a very compact structure in its center. What's driving the energy and luminosity of these galaxies has not been known. It's been discussed, buried AGN and or a nascent starburst. What we found when we looked at this object with ALMA was something very surprising. We found that the high velocity gas from this dusty object was shaped or organized in a form of jet like this. and also where we have very clear velocity reversals along the axis of the jet. This can be modeled very easily as a swirling jet, a precessing jet. But of course, this is not the only method. It's not the only possible explanation, but it is the one that's the simplest to model. The jet is massive, the molecular mass is very high, the outflow rate is also very high, up to 30 solar masses per year, even if we estimate this quite conservatively. I mean, this is a fairly small galaxy. Its luminosity is only a few times 10 to the 9 solar luminosities. And the jet outflow speed is quite high for being such a small galaxy. It's very model dependent, but we're now estimating to be 600 kilometers per second. So what's going on? Well, we looked at this jet with ALMA, and I really, really love ALMA. Now we have 20 milliarc-second resolution, which is 2 parsecs in this object. And what we find here is this incredibly collimated, beautiful jet, which also still retains the velocity reversals that we've detected before. What we're suggesting for this are based on the fact that we see a rotating wind surrounding the jet. And the jet is turbulent, but that could be unresolved rotation. We have also determined that the jet is launched inside a radius of 0.4 parsecs. We have, as of yet, not managed to detect any radio emission associated with this very collimated jet-like molecular structure. The momentum flux is very high, 14 luminosities per C, suggesting that this is not radiation pressure driven. It's also not powered by star formation directly. So what we are suggesting is that either we have a hidden, unknown radio jet here that is invisible for some reason that we cannot explain, or this is a magnetocentrifugal structure very similar to what we can observe towards galactic protostars. If so, it is the first one of its kind outside our own galaxy. We suspect that this is an X-con, that is the out feedback, which is then driven and powered by infall, has driven out gas that has, up until very recently, obscured the nucleus of this object as a con galaxy. The age of this feedback is only about 1 to 2 million years, so this has been a very quick process. And to conclude also that this molecular jet is very different in its structure compared to objects that have radio jets, where the molecular gas is lining the radio jet, and the radio jet is going through the disk, pushing gas in the disk of the host galaxy. This jet in 1377 is perpendicular to the disk of the galaxy, and it has, as of yet anyway, no detected radio emission. So to conclude, we need to study luminous dusty galaxies because they harbor a phase of very rapid growth, and they are extremely important. Oops. I can stop sharing. For some reason, Java wanted to update here. You cannot see my presentation any longer, right?
We're seeing the thumbnails.
Interesting, something happened here. Well, I think I can just draw my conclusion. So let's hop out of that. So let me just conclude with saying that the dusty galaxies are extremely important to understand galaxy evolution. And the most extreme ones, part of these dusty galaxies, are the cons. The cons recently discovered are still unknown on what's driving them. It's unknown how they can have formed, how we can have column densities in excess of 10 to the 26 on scales of 10 parsecs, even forming like this. and how it's also very unclear how they can survive long enough for us to detect them. So what's hiding behind the dust? An accreting supermassive black hole, or a top-heavy starburst, or something else that we haven't thought about? The molecular outflows carry out dust and gas in the centers of these galaxies. And what we have recently discovered is that the cons have very collimated outflows, which is in contrast to expectations of dusty galaxies, where we usually see more wide-angle winds. This suggests that there is a different process at play here, which is more linked to the MHD disk winds that we can see in the centers of protostars. Thank you.
Thank you, Susanne, for a fantastic talk. We have time for a question or two. We're past the half hour, but we'll get in a couple of questions. If you raise your hand, we can do a video questioning, or if you want to type it into the chat window.
Everyone's stunned.
All right. James Webb is right around the corner. Is there anything in particular that you're very excited about here?
Peter, I think I missed your, did you ask me a question or someone else?
Yes, since nobody else has any questions, I thought I'd ask with James Webb right around the corner.
Oh, James Webb.
What are you most excited about?
Oh, I'm so excited about James Webb. And the reason for that, there are many reasons for that, but one of them is with James Webb, we can look at these objects, of course, in the near infrared, for example, and the mid infrared. And here we have, we can detect the vibrational excited HCN directly in the absorption lines on the 14 micron, for example. Now, we shouldn't really, remember these have column lengths of 10 to the 26. That means that we should not be able to see to their centers in the mid-infrared. But we seem to be able to do so, which suggests that the gas is in a disk outflow structure, where there will be angles where we can see to the core. In addition, there's a recent study using the CO absorption band at 4.6 microns that suggests that we can see gas of temperatures in around 1000 Kelvin. Now, at these opacities towards the center, we should not be able to do that. So how is that possible? And with James Webb, we should be able to first of all, really separate out the, well, obviously we have ices, for example, that get in the way, right? CO ices. So we should be able to separate all the features from each other and get very accurate temperatures determined. But if it's true that we can really see that hot gas, then the question is, how does that actually work? Are we getting the dust to gas ratio wrong? Why aren't we seeing the X-rays? Because we looked at the cons with NuSTAR, and we don't see anything as of yet, anyway. So it's quite depressing. So the cons don't seem to have any kind of X-ray emissions. We're trying to with gamma rays, but we have to wait for Fermi to collect enough photons. So James Webb is going to be a fantastic instrument where we can see the hot gas directly. But if we do, it means that we don't understand anything about what these objects are. So if anyone has any ideas on how we can get to we know that there are very high energy phenomena buried in there. If anyone has any ideas on how we can get to that, I'd be very interested. We're thinking about neutrinos, but any other ideas anyone could have would be greatly appreciated.
All right. We should probably wrap up. So Suzanne has a one-on-one slot later this afternoon and several on Friday morning. So if you'd like to discuss in more detail, please sign up on the spreadsheet. Meanwhile,
Give me ideas on what these cons are, please.
and thank you to both of our speakers for some fantastic talks.